Okay, welcome back to Computer Organization Architecture, Week 6. So today it's the 11th, and had to schedule this online class since I couldn't make it for on-site. So please watch this video in this whole. You'll be responsible for the content, and I'll be going over some microcode instruction stuff. Also, just to mention where we're at. Wow, my network is going really slow. So basically, this is week 6. There's a test on week 7. The test will be made available on Tuesday, and it will be due on Wednesday, I believe. Let's double check that. Whatever I said in the syllabus is what is true. It's an online test, and there's going to be a couple different sections, multiple choice, short answer, and a breadboarding section. The multiple choice will be taken as a quiz, basically, on D2L, and then the short answer you'll just submit, and the breadboarding, you'll have to take pictures of your work that you complete. So okay, I had to restart my internet connection here. Anyway, yeah, we're going to make the test available on Tuesday, actually, and then it says that it's going to be made available on Wednesday, but Wednesday is actually the day I expect you to be working on it, and then you would turn it in on Thursday at midnight. So that's what's going on with that. Now let's go over to the slides. Okay, so this is just an adaptation of Commer. I added a couple things, especially where possible, to talk about x86 code and that kind of thing. And this is from chapter 7 of Commer. I'm actually going to record in this mode so you can see it in its entirety. Okay, so instruction codes work by basically having a big long string of zeros and ones. And some of those bits are going to represent the instruction, which is what you see here. For example, some are going to represent the operands. So for example, add A, B, C might be something like opcode 1010 with 3 different operands. Move A to B might be something like or move B to A, rather. You have to read it backwards. Move B to A, move load B, for example. So moving B over into the A position might be 1 0 0 0 and then 0 0 0 1. When you have a load command like load B, that just means that it's loading into the accumulator. That's what ACC stands for. So it loads directly into the accumulator. If you have an add command that only has 1 operand, that would mean that you add that operand into whatever is in the accumulator. Store would mean that you take from the accumulator and put into whatever variable name you give it. As we get down to 4 bits, for example, just an opcode, that would be like, and 2 bits for the operand, that would be things like push B, push C. You can even envision a world where we just have an add, where we add the last 2 on the stack. So what should the ISA and processor be able to do? Well, basically they should be complete. We should be able to have a rich set of instructions. When we chain this all together, I mean, it's like Legos, it just builds all upon each other. And it should be able to perform its required tasks. Well, its required task for a PC, as I said, should be a rich set. We have to build all kinds of things up together. Say for a gaming console, it would be a little bit different because it would involve more instructions that centered around the graphics of the gaming console and maybe memory management and that kind of thing. Microwave oven would need another limited set, and that would be even more limited than the other two. One of the other things we want to do in addition to being complete is we want to be orthogonal. It would be nice to minimize the amount of overlap in instructions because it makes it easier to understand as well as easier to program. We want the minimal necessary instructions for us. Otherwise, we have to maintain all of those instructions inside of the instruction set architecture. So the smaller the set, the better, as long as it can generate everything we need it to generate. Having more registers generally speeds up the CPU. But if we have unused registers, that's taking up space that could be used for something else. So, and which could mean that your onboard memory gets pushed further from the CPU and you've got slower memory speeds and that kind of thing. So you can't ultimately just have a ton of registers. You want to have a good mix of registers, onboard memory, and disk memory. And the processor does need to be backward compatible. The instruction set itself needs to be able to run on multiple versions of that architecture. So for example, x64 can run 32-bit code. So what it does in that case is it just simply uses the first 32 bits of that code. So that's an example of being backwards compatible. We also have to decide when we're designing these things what types of data is going to be dealt with. Are we going to allow for floating point? Are we going to allow for characters? What about interrupts? What about conditional instructions? All of those things need to be considered carefully. So we're going to start relatively simple. We're going to start with a memory module which is 64K to the 16th bytes of memory, each byte having 8 bits. And I/O is a memory access, so it's memory mapped I/O. We will also start with 3 registers. One is the accumulator, which will be used for the operands and the data loaded to and from the accumulator. And then we'll have one general purpose register, which will be labeled R. And then we'll have a 1-bit 0 flag Z that sets when the arithmetic or logic instruction is executed, and 0, for example, result in setting flag to 1. So this relatively simple CPU that we've just now discussed could have a variety of instructions. Could have like a no-op instruction, in which case it does no operation. It could have a jump, it could have an add, it could have a subtract, it could have a load AC, store AC, move register, add, subtract, and or not, all of those various things. An instruction with a memory reference requires the 3 bytes. So basically we have an instruction, a memory reference, and the address. So for example, we're going to store the address bytes with lower order bytes first and the higher order bytes next. So on one line we might have, for example, line 25, jump 1234H, or 25,000,0101. So again, this simple CPU that we're talking about would have just the instruction code, then the lower 8 bits and the higher ordered 8 bits. So we use gamma to represent the full, or at least the part of the address. So the lower 8 bits of that memory address and the higher ordered 8 bits of that memory address. Here's another microprocessor design. These are data movement instructions for the 8085. So the 8085 allowed, this was a computer, an older model before, well, way before the things like the 286, the 8086, and all of that. This was probably from, I'd say, the mid 70s. And it had some very simple instruction sets that did simple things like movements, pushing and popping from the stack, and that kind of thing. So it's important to understand the instruction set, the instruction format, so that once we do get to assembly, which is coming up very soon, we realize that all of these are simply just orderings of bits and bytes. And each processor is going to have its own instruction format. These are data operation instructions for the 8085. Program control for the 8085. These are our jump commands and whatnot. Okay, so now that we've talked about program control instructions, we should probably discuss a little bit about the idea of a basic privilege scheme for these things. This is a topic that's discussed a lot in the operating systems class, which is being offered next semester, for example. All of these commands that we're talking about operate on the application level. So some commands are going to be executed on the operating system level, and therefore, when we're coding up with our codes in x86 in assembly, we'll have to realize what the privilege scheme is that we're operating under. For the most part, we're going to be at the application level. Every once in a while, we might do something at the OS level. The micro instruction set, for example, is hidden from the programmer, because what's going to happen is the operating system has its ways of doing things with the registers and everything like that, and we are coding at the application level. We have visible to us a set of macro instructions that are implemented in the microcode. There are going to be a bunch of instructions that essentially are internal to the operations of the processor. So all of these commands that we've seen before are instructions that the programmers have available to them. And there's another level that's made available only to the OS and is called the micro instruction set underneath that. So for example, when branch prediction and control of our codes are done in the microcode, that code is organized in such a way that makes it optimal and pipelining can occur. That is done at the microcontroller level. So all those topics we discussed in chapters 5 and 6 that talk about how to best organize assembly and the organization of the assembly that occurs at the CPU level, that's actually all done down here. So here's an example of microcoded arithmetic. This microcode basically says, okay, how do we code up add 32? How do we make add 32? Add 32 is adding 32-bit integers. How do we get that to work at a microcode level? Well, we can move the lower order 16 bits from R5, for example, into R2. These are going to be our registers that we use for microcode instructions. Then we can add the R2 and the R3 and place the result in R1. Put in the carry indicator and then go on. So this is sort of an example of add 32 being a macro level instruction that can use microcode to achieve its results. So as you can see here, there are macro general purpose registers, which register access is provided for. The ALU also has its result that has to pass to these registers. And data can move between any of these functional units shown on the path. So as the ALU gets done doing its job, it passes the result in to result 1, which ends up going into the macro general purpose register. So the ALU has sent these microcodes as commands. For example, add, subtract, multiply, divide, left shift, right shift. And the operands are going to be loaded from the data transfer mechanism, which is either going to have like a register 1 or register 2, for example. It's also going to be able to communicate with the macro registers through the result of putting that on the result stack and then sending it to the macro registers. So this is an example of microcoded instruction. We see that the ALU would have its operation, and there'd be an operand, another operand, and finally a result. So instruction 1 might have a certain ALU value with a certain operand and an interface to the register. The interface to the register codifies how we communicate with the macro level registers. We also have the ability to do a continue, which just simply continues the previous operation that took place the previous time cycle, which is just a operation 111 and do nothing additional, essentially, which is separate from a no-op. A no-op actually will do nothing, whereas an ALU operation of 111 will continue the previous instruction. So for example, for parallel execution, we could say that operand 1 here is loading the value from register 7 into operand unit 1. So that's an example of an ALU command. And finally, this is just an example of what this actually looks like at the x86 and 64-bit level for the microcode. We have the header of the code, the update revision, processor signature, and then finally the data itself down below. So you see that basically the first 24 bytes are taken up by extra stuff that determines what type of hardware it's running on, what the checksum is. And the data is down here. So this is the part that has the instructions, is below the data. And then the reserved part, that's an extra 12 bytes. So when you think of 64-bit, you're actually not using 64 bits of data. You're using basically 36 plus a bunch of processor checksums and that kind of thing. Now that's at the microcode level, of course. When you actually store numbers at the macro level, you are allowed to store 64-bit numbers. But those store as in the registers as 64-bit. This is talking about the microcode itself and how the microcode looks, which would be stored in the processor itself. As each instruction comes in, it would store this instruction, interpret it, and if a 64-bit register is referenced, that reference is going to happen down here in the data section, and it's going to say that that 64-bit, what the location, that memory location is of that 64-bit location. So, all right, I know some of this is some pretty dense stuff, some pretty dense topics, but hopefully that provided you an intro to how this all works. I think the important thing of this chapter is understanding that at the top level, we've got our instruction set, which we've talked about a little bit before. But we've also got this idea of microcoded arithmetic, which sits below it and is actually doing operations on the ALU itself. So it gets even more complex than what we had discussed in chapter 5 and 6, because there's, if we think about it this way, let me draw up a OneNote here. Layers of processor. I'm just going to call it layers of computation. So at the top level, we've got our C++, our Java. Well, let's not say Java because that's gets into some complexities. Let's say C++. This is our high-level language. Then we get down to high-level language. This gets compiled. I do have a nice thing that lets me search shapes. I don't know. Here we go. Our high-level language goes down to compiled, executed. This means it goes down to the, well, let me just take this guy here. It doesn't let me just copy that. Oh well, fail. C++, and this gets compiled and executed. Then this goes down to another level. So we've got our C++. We're saying compile that and execute it. What do we compile it as? We compile it as assembly. And so that assembly, it can't do anything with that yet either. So we actually need to compile that down into microcode. Oops, wrong one. So this goes down to microcode, machine instructions, which then can finally get down to the ALU level. This is sort of the big picture. Yeah, so that's basically it. We start at C++, we go down, we compile it and execute it. That turns into assembly. The microprocessor is what actually turns the assembly into microcode. So it has to take those and it has to have an instruction set. So really, here what I should say is the instruction set is interpreted, well, actually executed. I want to be careful on my usage of the word interpret. The instruction set gets turns the assembly into machine instructions, and that gets sent to the ALU. So there's actually, to go along with this, there's actually a pretty cool thing called assembly.ynh.io that basically takes C++ code and turns it into assembly. And here's a bubble sort. So we're going to turn this bubble sort into assembly. We're going to use GNU C for it. Actually, let's use GNU C++. And so this ends up being the assembly. So we've got some push operations, a move operation. I mean, you can see that eventually you'll come to understand this. These are the, this is the global section, for example, that's declaring the bubble sort data section, which is then going to declare the various subsections that define our program. The reason we need this is because eventually you'll see that there'll be JLE instructions like JLE point L4. That means jump to L4, which is here. So that's an if statement basically that jumps to this. And this has one that jumps to L5. This looks like it's an incrementer. You can see that each of these was translated to a line number and a memory reference. That's what these are here. So that's about all I wanted to show for today. And we will see you in class on Thursday.